I'm going to be doing the AP Physics C 2019 FRQ Set 1, Number 2. A pendulum of length L consists of block 1 of mass 3m attached to the end of a string. Block 1 is released from rest with the string horizontal. At the bottom of its swing, block 1 collides with block 2 of mass m, which is initially at rest at the edge of a table of height 2L. Block 1 never touches the table. As a result of the collision, Block 2 is launched horizontally from the table, landing on the floor a distance 4L from the base. After the collision, Block 1 continues forward and swings up. At its highest point, the string makes an angle theta max to the vertical. And we're going to ignore air resistance and friction. Okay, so right now, we are going to try and determine the speed of Block 1 at the bottom of its swing. We can use the conservation of energy here. So the energy of the block over here, it's not going to be, let's say that it's not going to be moving. Like, let's say that the energy is right before it starts to move. So there's not going to be any kinetic energy, but there is going to be potential energy. And potential energy is relative to a height. So we're going to have to set a height as 0. Let's say that this height is 0 over here. H equals 0 here. Well, if H equals 0 over here, then that means that H is equal to L over here. So potential energy is mgh. We can replace every variable. So the mass of the block is actually 3m, and then g, and then we have h, which is L. And as we've already said, no kinetic energy. Over here, we've already established h to be 0. So if h is 0 over here, then there's not going to be any potential energy relative to this. There is going to be kinetic energy, which is what we're going to try and figure out in order to get the velocity. 1/2 3m squared. Well, anyways, the 3m cancels out. And then if you rearrange this, you get that v is equal to the square root of 2gl. Great. So that's our answer for part A. Now let's look at part B. Determine on the dot below, which represents block 1, draw and label the forces, not components, that act on block 1. Just before it makes contact with block 2, each force must be represented by a distinct arrow starting on and pointing away from the dot. Okay, so we have a dot here, and it's referring to the block 1 over here, right before it hits the thing. So there's going to be gravity and there's going to be tension, and those are the only two forces that are acting upon the block. Now the thing here is that we need to figure out the magnitude. We know that at this point the block is still accelerating, if not only because it's changing direction. And so it has centripetal acceleration, it has centripetal force to it. And centripetal force is just the force that's pointing into the circle. So into the circle would be upwards. And if there is centripetal force, then that means that there is a net upwards force. So we know that we have gravity pointing downwards and we have tension pointing upwards, but in order for the net force to be pointing upwards, that means that the upwards force must be greater. So that means that tension has got to be larger. Tension, I'll say tension, and then force of gravity. Hopefully it looks like the vector of tension has a larger magnitude, but that's what it's supposed to be. Okay, now let's look at part C. Derive an expression for the tension F of t in the string when the string is vertical just before block 1 makes contact with block 2. So we already said that there was tension up, and then gravity down. Gravity here would be 3 mg. And so the net force is going to be equal to the centripetal acceleration. So T minus 3 mg equals 3 m v squared over r. Okay, so well, we know the velocity just before block 1 hits block 2. We just did that. It was square root 2 lg. So we can just plug that in. So we move everything over to the other side. We get 3 mg, t equals 3 mg plus 3m v squared would be 2 lg. And r would actually be L. So these two cancel out, and you end up with 6 mg. That's supposed to be a G. Hold on. Okay, that's great. Yay. Now let's do part D. So parts D through G are going to be a little bit more about the kinematics. So calculate the time between the instant block 2 leaves the table and the instant it first contacts the floor. So when block 2 leaves the table, it's only going to have a horizontal component of velocity. It's only going to have a horizontal component of velocity. It's not going to be moving up or down right when it hits the table. Okay, that means that we can figure out the time taken using kinematics. So what do we know and what do we want to find? We know let's take a look at the vertical component. So we know the vertical height that it travels. We know h. We want to find t. We do know v naught because this is in the vertical direction, so v naught is going to be 0. And we know the acceleration in the vertical direction. So let's use this equation. Delta x equals v naught t plus 1/2 a t squared. Okay, so I believe that we do know, so delta x is going to be the distance. We're looking at the vertical component only, so from here to here, the vertical component is going to be negative 2L, because it went down by 2L. Okay. So we can just say negative 2L, and then again, the vertical component of velocity is 0, so it's going to be 0 plus 1/2, and a is going to be negative g, because it's pointing in the downwards direction, and then t squared. And then they give us that L is equal to 0.75. So if we just rearrange everything, t is equal to square root negative 2, 0.75 meters. They give it to us in centimeters. We want it in meters, so it matches everything else, over negative g over 2. And then let's just plug that into the calculator for a quick second. So After plugging it into the calculator, we end up with 0.55 seconds. Great, wonderful. Part E is calculate the speed of block 2 as it leaves the table. And again, we know delta x. Let's look at the horizontal component. So we know the horizontal component of delta x as well. And we also know we want to find the velocity, and we know the time that it takes. And we know the acceleration because it's the horizontal component, acceleration is going to be 0. So delta x is, I believe it's 4L. It lands 4L away. So 4L, we use the same equation as last time, equals VT plus 1/2 AT squared. But A is going to be 0 in the horizontal component, which, so V is equal to 4L over T. And then you plug everything in, and you end up with, let's just plug 0.75 over 0.55. Put that in, and I think you end up with 5.45 meters per second. And that's our answer for this part. For part E. Okay, calculate the speed of block 1 just after it collides with block 2. So this is going to be a momentum question. So, because it collides. And so let's say let's say that the system is block 1 and block 2. So right before block 1 hits block 2, only block 1 is moving. So we calculated the speed of block 1 earlier, and it ended up being square root 2GL. So all we need to do is, so the momentum the total momentum right before it hits block 2 is going to be 3m square root 2GL, because this is the mass and this is the velocity, and block 2 hasn't started moving yet, so it's going to be 0 plus 0. And then after it hits, it's going to be 3mv, and we're going to try to figure out what v is, and it's going to be m. This is block 2 now, and so we just figured out that the velocity of block 2 as it leaves the table is 5.45 meters per second. So we can just put that in, 5.45. We can just cancel out the m's now. We can plug in g equals 9.8 and L equals 0.75. And to solve for the v, it would be equal to, move everything over, 3 square root 2 9.8 0.75 minus 5.45 times 2 inside. 2 times 9.8 times 0.75 minus 5.45 over 3. And then you plug that in, and that ends up equaling 2.06 meters per second. And 2.06 meters per second ends up being our answer for part F.